Okay, welcome back, everyone. Welcome to undergraduate seminar. I've been looking forward to this one all semester. This is exploring the QUAKE III fast inverse square root algorithm with Daniel Harrington. Daniel, take it away. Thank you very much.
All right. Hi, I'm Daniel. I'm a second year student in the astrophysics program at U of T. Today we're going to get into the QUAKE III fast inverse square root algorithm. So just to start off, to introduce it, what is it? It's source code from QUAKE III, which was a 1999 shooter game, multiplayer FPS. It was 3D and pretty genre defining. There's a lot of games now that'll be kind of Quake-like. It's a clever approximation of 1 over the square root of x. It's 4 times faster than the basic solution they had at the time, and less than 1% error. And it does some cool tricks with the C language, where we kind of fool C with undefined behavior, and we'll go into that later. And then it's got origins that are they were foggy at first, some parts are still foggy, and it's pretty interesting to see the history of it. So here's the algorithm. I'll give you guys a second to take a look at it. There's some interesting comments. Seems like the people who implemented it weren't even quite sure what was going on. But it really made waves when this first, was introduced. It showed up on Usenet forums in 2002, 2003. As a leak, and then ID Software actually releases the source code for all their games, so it was officially released around 2005. So we'll go through it a little bit step by step. For anyone who's not really familiar with programming, we have a function that takes in a number in the float representation, which we'll be talking about a lot today. And then we have some constants, long, a float, and another constant float. These are all 32-bit numbers, which we'll get into when we start talking about the algorithm. We have a few more constants, and then we have this first step, which if you're familiar with programming, you might recognize it's casting something to something, but it's got a bunch of extra things in there that probably aren't immediately clear. Then the second step of the algorithm has this strange hexadecimal constant minus what you might recognize as a bit shift. And then this looks similar to step 1, and step 3 is we're just multiplying and subtracting some things. And then we return our final value. That's how we get our approximation. So how they did that, we'll go through step by step. But first, why do we need it? So surface normals are really important in 3D games. They control things like how the lighting bounces off surfaces, stuff like that. And for anyone who's taken linear algebra, well, you know that a vector is 3 components. The absolute value of a vector is the square root of those components squared, right? The sum of them. And the unit vector, the normalized, we're normalizing it to a length of 1, is the vector over the absolute value. So you can see how we'll end up with an inverse square root here. Now, in games, especially 3D games, this is something that's calculated nowadays maybe millions of times a second. It is extremely, extremely crucial. So, we can't save time on everything, but this is something very important to save time on. So where did it come from? This is QUAKE III, the cover art, a screenshot of the in-game for those unfamiliar. I had, a reflective me or something, pretty exciting graphics for 1999. And it was a very, very popular game. Like I mentioned before, it showed up in 2002, 2003 first. And two big questions immediately became, the talk of the town. Who wrote this code, right? Because this is so strange. Who created it? And the next question is, what is that weird constant? So then the constant we're going to refer to a lot as the magic number. So this guy called Rizzard started a forum investigation in 2004, where basically he went around emailing everyone they thought might be the author of this code. And so the first suspect was pretty obvious. It's John Carmack, the lead programmer of Quake at ID Software. But they asked him, and it wasn't him. He said, I don't know. So the next guess was Michael Abrash. Michael Abrash was also a Quake employee at ID Software, but he was an expert in x86 assembly optimization. So he was an expert in optimization. But it wasn't him either. So they emailed Turge Matheson. Surely it must be him, because Turge Matheson is also a renowned optimization expert at this point. Whenever you're on forums related to those things, he'll pop in occasionally. But it wasn't him either. So they move on to the next possible suspect, which was this actually was part of the investigation. This is a little bit of an aside. So those numbers at the top, I maybe should have labeled them better, but it's how we're tracking it back in time. So this is an appearance of the code in 1997 in an IEEE column for computer graphics and applications. And this guy is James F. Glynn. He's a computer graphics expert, worked on the Voyager animations. He wrote a column on how to write this algorithm, something similar to it. It also showed up in a reverse engineered version of this 1997 game by Activision. So back to the investigation, we have our first real lead, and this guy is a pretty big deal. His name is Gary Tiroli. He's the founder of 3DFX. For those who don't know, 3DFX, they made it, their hardware and implementations is popularized or repopularized the idea of consumer graphics processing units. So not quite GPUs yet, but they could be credited with the reason we all have NVIDIA GPUs today is. So this guy, responded to Richard saying that, hey, I've used this a bunch. I probably am partially responsible for popularizing it, and I might have tweaked the constant for my own needs, but that was the end of the search. That's the dead end. We were stuck at Gary Tiroli. He did not fully write the code, right? I just used it a lot and probably made it popular. So this investigation got so popular that the real author came forward. And so now we know the real story of where this came from. And I think it's really cool that the start of this real story comes back to U of T. This is William Kahan. He got his bachelor's, master's, and PhD all here at U of T in math. And he's a Turing laureate for basically inventing the modern representation of a floating point number. So his paper on how to do this for the square root of x is the first time we kind of see this algorithm come to light in 1986. It's not inverse yet, it's just the regular square root. Then in the late 1980s, this guy named Cleve Moeller at Argonne Computer, another very pioneer software firm, shows it to his colleague Greg Walsh, and Greg Walsh was the author. Now, kind of fitting with the enduring mystery of this code, he was the only one I could not find a picture of. So what about the magic number? We still don't know. The oldest reference is in a Bell Labs manual for Unix 5 or PDP-11 Unix. And it's through a PDP-11 system up there to give you an idea of how old that is. All right, so into how it works. This relies heavily on the float representation of numbers. So we're going to spend a while on that before we can jump in. The actual algorithm will go by kind of fast. If we understand, how they're playing with a floating point, it'll make a lot more sense. So for those, because if anyone hasn't seen binary before, and binary numbers, we have 0, 1, 2, it's base 2, so you can go from 0 up to 1. Once you hit 2, you need to carry over, right? Same as in 10, base 10, we can get to 9. Once we hit 10, we carry over. So this is 32-bit long. It's nice and simple. It's long, it's a long integer. But there is a bit reserved at the end for the sign bit. So if it's 0, it's a normal, it's non-negative, it's 1, it's negative. And this can be in this range, it's very, very, very large. Now, this is the crux of today's topic. This is the IEEE 754 standard for floating point arithmetic. So we have a sign bit, just like in the long. We have an exponent section, and we have a mantissa. So mantissa you might see referred to as significand elsewhere, but we're going to call it the mantissa because it sounds much cooler. And it both show up in the text. So what this does is think about scientific notation. Okay, this is a very clever way. So we don't want to just put numbers before and after a decimal. We can use the tricks of scientific notation kind of to make this work. So we have the mantissa as a fraction. Okay, it starts at 1/2 and we go to 1/4, 1/8, and so on as you go down the mantissa. All right, and then we multiply that by an exponent minus a bias. So 2 to the power of whatever number is in that exponent bracket minus a bias, which here will be 127. And to be clear, the reason there's no 1 in the start of that is because in binary, right, we either have in scientific notation, you always have a 1 leading your number, right? 1.7, or you have a non-zero number. Well, in binary, the only non-zero number that would be leading it, if it's not the number 0, is 1, right? So we save a bit by just assuming that's there, and we'll see that in the mathematical version of it. So we'll let m represent the mantissa's actual integer value. So like if we just took that number and, just took a number and stuck it there, and note that m over 2 to the 23, so divided by its length, we get a number between 0 up to 1. We can't quite hit 1. We can hit 999, right? Or 0.9. And then E will represent our exponents. So that set of numbers right there, right? If you were to take them by themselves, they could give us a range of values from 0 to 255. Now we're working with a special set called the normalized numbers when referring to this algorithm. So we actually, the first bit will always be, we can't have all zeros in that. There needs to be a 1. And then the all ones is reserved. It's reserved for infinity. So our actual range is 1 to 254 for that E. Right? So that's just the exponent section and the mantissa section. So the way we get this, the bit representation of this number. Oh, I apologize. Those that should be decimal representation. I'll just skip the slide where it's the right thing. So for a decimal representation, to make this a little clearer, we have -1 to the power of the sign bit. So if it's 0 or 1, this will be positive or negative, right? And then we have 2 to the power of whatever is in our exponent section. So remember, it goes up to 255, but ours will only go to 254, minus 127 times that 1 we omitted earlier, right? Because of the trick in binary, plus whatever fraction our mantissa is, right? So if we take the mantissa and divide by 2 to the 23, that's a number between 0 and 1. And the bit representation will be the reason we're doing this multiplying by 2 to the 31, 2 to the 23 here is just shifting them over. So if you have this number, you want to shift it over to the left, 22 spaces. Well, there are 23 spaces. That's how we're going to do it. So thankfully, today we don't need to worry about the signs because this algorithm normalized numbers and they're also going to be positive. So we don't need to worry about the sign bit. Just keep an eye on these. This is the decimal and the bit representation, okay? Keeping these in mind, now we do something a little strange. We look, I want to introduce to you this interesting relationship between the two that's kind of hidden in logarithms. So if we take log base 2 of both sides, so log base 2 of the decimal, right, equals the log base 2 of what, how we achieve that number. Well, using log identities of, the product of two things, the log of product is the sum of them, right? So we have log 2 of 2 to the e minus 27, or 127, plus log 2 of 1 plus m over 2 to the 3. And then, well, the first one's pretty easy, but we're stuck with this log base 2 of 1 plus m over 2 to the 23. Now, for anyone who's done some physics or stuff like that, you might have heard of the small angle approximation. There's something fairly similar for logs, where log of any base of 1 plus x for a sufficiently small x is a really good approximation of x plus some tuning value we'll call sigma, okay? So if we use that, apply that, we can get rid of the second logarithm. And then it might not be immediately apparent, but let me rearrange it a little bit for you. And you'll see that we end up with this. So if you look, this is pretty exciting because our bit representation is inside of the logarithm of our decimal representation. So in some ways, our bit representation is proportional to the logarithm of our decimal representation. It's just scaled and shifted by a little bit. So why do we care about the logarithm? Why is this, this is kind of a neat thing, but why do we care? Well, we have this identity where the log base of any base times x to the a is a log b of x. So we have, for log 2 of this inverse square root of x, it's equal to the negative 1/2 of log 2 of x, right? So if we can get that log 2 of x, we can get the square root. Oh, and I should have mentioned this earlier. Our goal here, floating point numbers, so working with floating points in terms like mathematically, is very computationally expensive at this time in history, okay? And also division. Division is also very hard to work with. So these things are very computationally expensive. If we can avoid them, we would save a massive amount, okay? So I mentioned earlier, but this is our goal, is to avoid doing any division, avoid doing any working with floats or doing math with floats as much as we can. So now we rearrange, we plug in, if we want an approximation of the, so I'm just going to move this up here a little bit. Yeah. So now if we want to get an approximation for whatever one of the inverse square root of x, we will just plug into our formula. and we can rearrange a lot. Now, I'm not going to go through all the rearranging. I'm going to leave it in the slides because most sources just say I'm not going to go through it and then don't show you it. But I did work through it if anyone wants to go through it. So we plug our representation of inverse square root, right? And we say it's this, and we just keep rearranging, and we get through all of this, and we end up with this. So we end up with our bit representation of y is equal to 3/2 the length. So if you see this L, just know it means 2 to the 23. Okay, we're just doing the length of the number. So 2 to the 23 times the bias minus sigma. And then that whole term minus 1/2 of the bit representation of x. Okay. We found something extra cool because this can actually be used for any exponent other than p, or other than negative 1/2, with this formula down here at the bottom. All right. So, if you're wondering how accurate this can be, we haven't quite earned this approximation yet. Or this accuracy yet, but just to kind of get you excited, this is with a suboptimal value of sigma. This is how close it is. You'll notice you can barely see that. I'm not even sure. If you looked really close, I'm not sure you could see the difference. This is the difference between the actual number and the approximation we have here. But we haven't quite gotten to earning that yet. So we'll go back to the code and we'll start with step 1. So accessing the bits. We need a way to manipulate the bits, and long or floats actually don't allow you to do that. You can't do a bit shift or things like that on a float, or at least you couldn't at this time. So we need another way of working with this that'll let us do that. Fun fact: this is not only was this undefined behavior in C at the time, it still is. So there is another way of doing this in C. This does still work. I have tried it.
Just to be clear, what is it supposed to do?
Oh, I'm going to get to that.
Okay.
What's it supposed to do? Yeah, sorry. That's I will get to that. Don't worry.
My C is very restless.
No problem. This is not a matter of mastery of C. This is a matter of knowing what this weird trick does.
Okay.
So, what this does is if you were to just print out cast to long. So what a cast is, for anyone unfamiliar, it just changes one type to another. If we were to just cast this to a long and print it out, well, you take a look here. Y casted to long. If y was pi, well, I just get the number 3 back, but that's not what I want. I don't want to lose my accuracy, right? So what we do instead is we use pointers, which in C are just kind of like putting a tag on things, right? Where this is here, this is here. And what we do is we convert the memory address. So think of it like switching tags on something. And you switch those tags, and whoever has to read those tags is absolutely convinced. So I use the example of an employee, but like think of the grocery store. If there's a label for like carrots and a label for cabbages, and you switch them, and whoever reads them now is absolutely sure whatever here is a cabbage, and they will treat it like a cabbage even if it is a carrot. So this code snippet returns a very, very different number, right? So that's what step 1 is. It's tricking C into letting us read out that value as if it were a long without getting rid of the accuracy we have. Okay.
Wait, go back. So this 107,853. What is that number? Like, is that just the memory address of that float, or is that actually related to pi? It's related to pi.
So you pick the floating point representation of that number. So you say, oh, I pretend, oh, so then you change your mind. This is not a floating point number. This is an integer.
Right. Oh, so that is the
So take the bit pattern,
the bits.
but you interpret it as an integer rather than a floating point number.
Right, so all the business with mantissa and sine and exponent, I just forget that. I'm like, this is just a 32
Yeah, so
binary
this
number.
is.
Yes,
so
exactly.
We have the notation x back and x bits. Yeah, x subscript that. So this is converting x subscript back to x subscript bits.
Got it. I think I got it. Okay.
Yeah, sorry, it's a little tricky to show exactly like the conversion. And that's the end of step 1. That's all it does. It's just lets us get at the bits in that interpretation of them. So step two, we need to apply a little bit of our knowledge. A fun fact I ran into this OX here. So anyone hexadecimal is just a number in base 16. The way you signify it, I'm about to say a hexadecimal number is with the 0x in front. And this 0x was actually changed to a 0 when B was written, the predecessor to C. C was originally called new B, so I applaud them on the creativity of the rename. But it doesn't look like anything we know yet, so this might look a little bit more familiar. So a bit shift to the right will half a number. A bit shift to the left, right, will multiply it by 2. So remember in that fraction how I said it was adding 1/2, 1/4, 1/8, and so on? Well, if you shift it to the left, to the right one, then you end up adding a 1/4, an 1/8, and so on, right? You don't, the half gets cut in half. So a bit shift to the right will divide a number by 2. So if we bit shift to the right once with this number, we get, and we subtract it, we have minus 1/2 x. It still says int here. It should say decimal representation. I apologize. Integer decimal. A lot of different words get used for this, and there was some mix up. But so what we have here, if we break it down a little bit, is the now interpreted as an integer version of x. Bit shifted the right one, so we have negative 1/2, and then we have this constant we'll call c. So C is the tricky thing, and we're not going to go into a solution for C here. There's a lot of different solutions, but I'd like to highlight the problem. Why do we need, what is our correcting term dealing with, and why is it so hard to find a good value for sigma? Well, there's a few situations we think about here. So you might have noticed when we shift our float 1 to the right, for odd exponents, we push a 1 into the mantissa. So we're adding 0.5 to it, right? So that's, it's only 0.5, but it's going to get multiplied by whatever our exponent is. So that's a problem. And for our exponent, we end up with 2 to the power of e bit shifted to the right minus 127. So we're cutting our exponent in half as well and subtracting 127 for it. Okay. We could also lose a 1 from the end of the mantissa during a shift, but this is going to be much smaller. Still an issue, but much smaller. And then I wanted to write this out a little bit more formally for those who prefer it that way. Hopefully I translated it well. I'm simplifying a very, very mathematical definition in Moraz et al., a paper on this topic. But basically, I wanted to break it into these cases. So the important thing here is we're rewriting ex lowercase and mx to just represent the term at the top of that exponent, right? The exponent term we end up with after the bias, and mx will be the whole mantissa after we've added the 1 back. Where our values are between 1 and 2. So it breaks into these cases for what happens after our shift. So for even exponent before the shift and a 0 mantissa before the shift, we end up with the exponent becoming negative 1/2 what it was, and the mantissa remains 0. For an even exponent and an even mantissa, or an odd mantissa, we end up with the latter exponent being negative and minus 1, so we lose 1 from it. And then the mantissa being 2 over the root 1 plus mx. And then we have the same result for odd exponents with the non-zero but even mantisses. Now, these are kind of hard to work out algebraically, but I wanted to show how our cases shift and just highlight the problem that our constant is solving. Yeah, so for the notes about this is you can see that the exponent is at least twice overpowered by the bias. We might lose an extra 1. For even ex, so for even the full term, we shift a bit into the mantissa, adding 0.5. Even ex, interestingly, if you have an odd capital ex, you have an even lowercase ex. So that's a bit funky to work with. And then I just, for the odd ex and odd mx, tried to work out for you how that one appears. So while we're searching for a new magic number, we can actually get really, really close without sigma mattering so much. Sigma is actually tiny, very, very tiny. Okay, we can set sigma to 0 and get very close. So with sigma is 0, we have 3/2 times the length and 7 minus sigma, and then we end up with this big, huge number. If we convert that to hexadecimal, we get 5f to the 40,000, or is it 400,000? 400,000, yeah. And then if we write this as if it would be in code, we'd add our 0x, and we can see this is really close to the magic number from before. Right, we have that same 5f, the dominating terms at the front are very, very, very close together. And the reason for that is the original magic number, the sigma value is only 0.04504665. So we'll use that for the rest of this. We'll just to keep in the spirit of where the algorithm came from and stuff like that. We'll use the magic number from here on out, or as if we've used the magic number. So it's kind of hard to see. Can I zoom in at all? I want to yeah, I can zoom in. Perfect. So you can see this is our first guess. So compared to the green is the inverse square root of x, the black is our approximation. So we're very, very, very close, but not close enough. Not close enough. There's you still end up with problems in lighting if you use this number.
Do you have the graph for sigma equals 0? Like if we just went with like, okay, let's ignore sigma. How far off is the graph then?
I can get the graph up.
Okay. If you don't have it in the slides, don't worry about it.
Yeah, sorry, I don't have it right in the slides. Trying to think. It's it is still very, very close because this that approximation of log, the earlier approximation, the small log thing, between 0 and 1, the difference is very, very small. And that's kind of what this relies on, right? So it would be somewhat small to begin with. But yeah, that's a good point. Sorry, I will leave. I have links to all the graphs on Desmos.
Nice.
So anyone who wants to play with them or try them out later, their errors graphed as well, then you'll be able to. Stop working, or did I click on something? There we go. And that's all step 2 does. So step 2 is really just applying all this knowledge we have from before. Step 2 isn't doing a ton of math. It's just it takes a fair bit of math to get to the understanding where we can do this little trick, this little step to the right with the bits and a constant. So this is where our approximation is at now, and we get to Newton's method. So this is fun because it's something that I'm sure lots of people have seen before in Calc 1, and the Newton's method, for those who don't know, is a root finding method. So it gives us, if we have a good initial guess, which as you saw before, we have a pretty good guess. If our guess is good, then applying this formula of our new guess is equal to our old guess minus the function over its derivative, then xn plus 1 will be a better guess. But as you can probably see, what we have at the top doesn't quite resemble that yet. And here's a graph for anyone having trouble visualizing that, how you see how xn and xn plus 1 is quite a bit better. So zeros, why are we looking for zeros? I thought we're looking for inverse square roots. Well, we can define a function where the right guess is 0. So if we define a function f at y is equal to 1 over y squared minus x, if you were to plug in inverse square root of x for y squared, well, you'd be squaring it, so you'd have 1 over x, and you'd have 1 over x, which means you'd have x, right? So this number is only 0 when our guess is perfect. So if we apply Newton's method, we have this, and then we're going to take the derivative of our function, right? Which just looks like that. We have the -2 y cubed, and then rearranging a little bit, we get y plus y cubed times 1 over y squared plus x over 2. We can simplify this even further. So I'll give people another second to look at that if they want to try and work it out a little bit. I don't want to speed through this part too fast. And then the next thing we're going to do is we can simplify a little further by separating out the different terms. So we have our new guess is equal to y plus y divided by 2 minus y cubed times x over 2. And if you remember the code, we're getting a little bit closer now. So let's factor out a y. We have y times 1 plus 1/2 minus y squared times x over 2. Which, we can combine the 1 and 1 over 2 to get 3 over 2, right? And then this looks a lot more similar to the code we have, where our new guess is equal to y times 3/2, which I want to take as an aside. I think it's really funny they decided they needed to declare 3/2 as a constant and explain what that was. But x2 there is half of x. They didn't explain that, and they didn't explain the magic number. No one knows to this day how it was derived. I wanted to, as recently as like 2010, people have made attempts. The 2020 paper I referenced earlier, Marov, they asserted that it was guess and check. I want to say I disagree because it's the original number. So the reason I called that earlier sigma I showed with the not the second one but the first one, the reason I called it suboptimal is after this step, after the Newton's method is applied more than once, it's less accurate, which is pretty crazy because that suboptimal one I referred to is actually considered the optimal one if you approach this problem through approximation theory. But the magic number beats it. And yeah, that's pretty neat. So this is our new approximation, and I'll zoom in again. So our new values are in black. So the amount of error we have at this point is pretty much non-existent. You can apply another step of Newton's method. That's what that commented out portion was, because it was just the same line repeated. It is pretty unnecessary though. There is a demonstration I've linked at the end where someone used this for ray tracing, and you can see pretty clearly there that the amount of error you get with 1 versus 2 Newton, it's almost non-existent. You don't gain much more for running it again. Yeah, and then we've gotten all the way through. I went a little faster. So I wanted to talk about why we care about it, and what's interesting, or what is it now? Where is it now? Well, now this algorithm is, for the most part, unless you're working on very exotic hardware, it's obsolete. So as of 2020, there's still people trying to find more efficient magic constants. And theoretical, like computer science stuff, it seems to still be a topic kind of at large. People, everyone wants to find the new best constant. But outside of theory, it's not really used. Why? Well, around 1999, new hardware came out supporting a processor instruction called R squared SS. It's an instruction for computing inverse square roots. It's about 4 times faster than this. There was a need for it, as we kind of highlighted earlier. So, people found a hardware solution. So I think part of the reason it's interesting, besides talking a little bit of the floating point representation and learning about that, one of the cool reasons, or one of the things I find kind of inspiring about the algorithm is it's kind of a reminder that it may be obsolete now, but it serves as a reminder not to be too hasty in assuming all the low-hanging fruit has been picked in our field. So a lot of the math we went through here, I realize this part in the middle is a bit weird and confusing. And it just is. Like if you try and look into this very analytically, it is very, very, like, it's weird. It's weird. There's a lot of things that can go wrong. It really depends on an idea of the floating point numbers. But up here, right, up here with the logarithms and stuff, all I did was apply like 2 log identities and rearrange. This is all like first year calc, the first few days when they hand you a sheet of things to memorize. It's none of this, this was just understanding the representation of what we're working with and then applying some first year math to it. And you can get a number very close. You could probably guess and check it to find a sigma value, because remember how close we were without a sigma value, right? Though I don't have a graph for that. I think it's interesting to kind of keep in mind, you don't need to be the next Fields Medal or Turing winner to create something like this. The guy, when we went through our the history, it may have passed through the hands of many computing pioneers, but Greg Walsh, as far as I know, is probably a very good one, a software engineer, and is very clever for putting this together in the way he did. But yeah, it just took someone looking at what they're working with very carefully. And they made a huge contribution, to their field and did something really interesting. XKCD's also got a fun comic that references. They actually reference one of the newer constants, so he must be very caught up on the topic. Yeah, I'll let you guys read that. But just things in business, kind of like, because this came from Bell Labs, right? Well, in academia, I'll zoom in more in the hold on. In academia, they get recognized. In business, sometimes these things go unnoticed, and it takes someone kind of looking into the topic or familiar with it to put them together in an interesting way. So for anyone who's still curious about the topic, because it is kind of hard to, if you really want like a very detailed idea of exactly how this works, like mathematically, it's going to be kind of hard to deliver right away. This is so. I've got some things I encourage people to check out it's not letting me. So these are just more things on the topic. So we have a ray tracing demo. This is about a minute long, but they just they use the algorithm in their own ray tracing software program. And it really does a good job highlighting the different stages of error. This is an interactive IEEE 754 tool. This is something I used a lot while preparing this to make sure I had an understanding of it. It basically lets you just check off the boxes where bits are and gives you the number it would output. This here is all these links are clickable in the slides, by the way. I don't know if they get uploaded before or after, but
yeah. So after the talk, I'll put these on the seminar website.
This is a graph of the accuracy at each step. Including a step we didn't talk about that was, because it's not part of the original algorithm, it's part of the modern optimizations of it. And then this is a GitHub for all of QUAKE III source code, so if you guys are interested in checking that out, it's this is where it was found, and it's kind of cool that it's just out there. So these are the things I definitely recommend you check out. If you are someone who prefers you want some more animation, stuff like that, these 2 videos here, this one is focused pretty much like primarily on that part about the constant and the shifting of the exponential value. They do a decent job highlighting in this, and this is a very nicely done animation that kind of explains everything up to Newton's method. It's a little bit higher level than what we went into today, but it animates the bits moving around nicely. So if you like visuals, this is a page that explains how or calculates the original constant or derives the choice of it. Sorry, they can't derive the choice of it, but they explain it a little, that stuff a bit more. The notable properties of scientific numbers, this is just a cool page I came across. For anyone who wants like a much more mathematical view of this, I recommend Eberle's investigation into it, the fast inverse square root, or if you want a really formal version, Morez et al. I was calling them Morov earlier. Morez et al. And Lomont is they're very mathematical, much more rigorous. And then this is the links to the investigation if anyone wants to read the emails between all those pioneers of computing. but I finished up a little bit faster than I expected.
That's great, yeah. Round of applause. Well done, that's sweet. So we've got two traditions. One is we need people's signatures for coffee and muffins. So I'm gonna hand this around. Can you just see how many people are online?
Yeah.
Just look at participants thing.
I think it's just the one.
We'll get a couple people, maybe go down to the Zoom toolbar. Yeah, I got, oh, we've got a couple people in. All right,
Great.
I'm gonna send the thing. Where's the chat? So for the people who are online, please fill out the following. Great, yeah, so please fill out the following, that gives feedback to the speaker, that's awesome. Yeah, now we can take questions and chat.
Yeah. Are there any questions? I do know more about it. So. Oh, I shouldn't mention that once we got to the end, I didn't mention it again, but you notice we got there without doing any division or messing with floats at all, minus the, a little bit of multiplication in the end, but they were constants, and that's kind of nice.
Yeah.
So yeah, it avoids all of that.
And one multiplication.
Yeah. Yeah.
Sweet.
Yeah, does anyone have any questions about the yeah. I can try my best to answer them.
So one thing that I find very striking about this, what do you got? You've got constant and a bit shift.
Yes.
Basically, that's it. Are there any other functions you can approximate this way? Right? Like, is there or is inverse square root the only thing people ever care about?
I think inverse square root was the one that got all the highlight, but like I said, the paper by William Kahan was originally on the non-inverse version. You could approximate. I don't see why you couldn't approximate other things, because it's just the logarithm, right? It's not the it's not based on the exponent. The part we based on the exponent was when we plugged it into the logarithm and rearranged a whole bunch. So yeah, that approximation should work for any exponential. Yeah.
Cool. Yeah, because it'd just be cool to, I don't know, I got this one very specific way of doing things, but maybe it's possible for more functions. Maybe there's other optimizations.
Yeah, this the part yeah, the part up here about it being generalized, that H store page, or by Hummus and Magnets is his name. He shows a walkthrough on how you can use this same approximation for, I think he used it for a cube root or something.
Okay. Oh, yeah, you had something with
yes, yeah, here.
Yeah.
So it actually works for any exponent p like that. Yeah.
I think people want to ask about.
How did you make the power? The PDF.
Latex in overleaf.
I think, yeah, the thing to look into will be like Beamer, BEAMER, relief.
Yeah, Beamer and overleaf. There's some nice templates that I think a few people have used. Looking back there, I recognize some of them after I was using it. So yeah. Yeah. Any questions at all? It's yes, it was replaced for an instruction just kind of built into hardware that CPUs now understand. I don't. Unfortunately I don't. When looking into it, it's hard to find like the system architecture behind a compiler. I'd probably have to dig a fair bit deeper for that. Because it's hardware level, I'm sure it's pretty wild. But yeah, usually when you look that up, you're going to get a bunch of people implementing it rather than or asking like how do they use it. Even if you like, because that's below even like typing it in an assembly, right? Yeah. So I don't know exactly why it's faster, but generally things in hardware are going to be faster, right? Because you think about like M.2 drives, right? Part of the reason they're faster is they're literally closer to the CPU, right? They have like a direct line of communication with them. So yeah, hardware is generally going to be faster because they've just set up a path for it at that point, you know.
Next week, we've got a speaker from the University of Tacoma, Washington, so it'll be online. And we're gonna learn about the math of juggling. Excited about it. It's kind of cool. So next week it's Eric 2 from Tacoma, and that'll be a virtual one. There'll be coffee and muffins as usual, so grab some of those, and it'll be next week.
It's gonna be a Wednesday one.
Oh, yes, yes, that's a Wednesday talk. Yeah, we've got one other talk on a Thursday, but next Wednesday, same time, same place, fresh out.
All right. Thanks for hosting it, Parker.
Yeah, thanks, that was awesome.
Hope everyone had fun.
Yeah. When people are like, oh, you can like brute force this or something, or find the magic constant by just checking all constants.
They have tried that, yeah.
They have tried that?
Yes, some people have tried that. There's so maybe I should have broadened it even beyond like different fields of math. They've used like number theory, approximation theory, brute force. Honestly, everything I can think of it just seems like they threw everything at it, and every time you end up with a different magic constant. One or two of them is better than the original constant. I think it may have been the brute force one.
Sure, because like I'm like, okay, you've got the first two digits 5 and 4,
Mhm.
and then you've got 4 did 5 zeros to fill out. So that's not a crazy number of cases. I think that's like
Yeah, yeah.
2 to the 10 cases, maybe 2 to the 30 cases. That's something that's like
Yeah.
It was like 5 more packages.
okay.
Oh, right.
6.
16 to the 6.
All right. Even if you ask the computer to stack 2 days. That's the worth it. 2 days is not very.
Yeah, I mean nowadays we can definitely do that, right? Because yeah.
But I don't even know what you want to do. Like, do you want to minimize the distance in the function? What do you want to optimize for? You check all cases, but what do you want?
Yeah, you have to figure out, what cases, showing up the most often, making the biggest difference, right? There's a lot of weirdness to it.
I like it. I like this mystery aspect of things. Usually we don't have talks that end in a mystery.
Yeah, it's yeah. I got excited for like 3 hours when I thought I found it, and I was off by like I think 11% of the sigma value. So like 10 to the it was like 0.3 times 10 to the -7 I was off by or something. Like I was like, no, I thought I found it. That was the first one.
Well, thanks, folks. Yeah, we'll see you next week. Yeah.
Yeah. For all.